This is John Whitaker for the graduate level probability class. And this is our 17th video lecture. And today the main thing we're going to talk about is the central limit theorem. I'm going to state it and prove it and also do one example with it. And the central limit theorem has to do with a type of convergence about convergence in distribution. And so I'm first going to define what does it mean to converge in distribution for a sequence of functions. So let's go ahead and get started with that definition and then state the central limit theorem and prove it and then do an example. So here's the definition. It says the sequence of random variables x of 1, x of 2, x of n, and forever, converge in distribution to a random variable x okay, if the limit as n goes to infinity of f sub x of n of a equals to f sub x of a, this is pointwise, where f sub n, f sub x of n of a is the CDF of x of n, and f sub x of a is the CDF, cumulative distribution function, of x. This in general is the weakest type of convergence for probability, and the top probability that we'll look at. Okay, so here's the central limit theorem. It says if x of 1, x of 2, up to x of n and beyond is a sequence of independent and identically distributed random variables with each having a finite mean, expected value of x sub I, but we'll simplify that with mu, and finite variance that's the variance of x sub I, denoted by sigma squared. Then the distribution of x of 1 plus x of 2 plus all the way up to the addition of x of n minus n times mu all over the square root of n times sigma in the bottom converges to the distribution of the standard normal random variable. Okay, so that's what the statement says, but I'm going to give a clarification of this statement. And the clarification is the following. That is the limit as n goes to infinity of the probability that x of 1 plus x of 2 plus x of n minus n times mu all over the square root of n times sigma. Probability that that's less than or equal to a equals to the integral, so it's 1 over the square root of 2 pi times the integral from minus infinity up to a of e to the minus z squared over 2, that's a 2, dz. And that's what it says. And that's true for every a element of R. So that's the distribution of the CDF for each n of the function that we're interested in, random variable we're interested in. Being less than or equal to a, that's what gives the CDF, that probability. So the limit of those CDFs converge to the standard normal's CDF. That's what the standard normal CDF is. Okay, let's do the proof. Now the proof is going to be based on a big fact dilemma that's going to relate the conversion in distribution to conversions for moment generating functions. But first, let's get the setup here. So we're going to let x of 1, x of 2, x of n, and beyond be a sequence of independent and identically distributed random variables each having finite mean expected value of x of I equal mu and finite variance and that's variance of x of I equals sigma squared. Okay, that's the setup. Okay. So the lemma that we need, if we're going to depend on, is the following. Here's what it says. It says let z sub 1, z sub 2, up to z sub n, and beyond, be a sequence of random variables where or whose CDFs are denoted by, or are, big F sub Z sub, we'll say N of T, and whose moment generating function are, so there's T sub x sub n of t. Okay. So that's what we'll do there. And then we'll let z be a random variable whose CDF is denoted by f sub z of t, and moment generating function is phi sub z of t. Oops, I wrote down x here and I shouldn't have. This should have been z sub n. If the sequence of moment generating functions converge to the moment generating function of z, then the sequence of CDFs converge to the CDF of z. Well, for all t where f sub z of t is continuous. Sorry, continuous, okay? That's the lemma that we're going to use. Okay, so that translates for what we're trying to show in the following statement. Okay, so we want to show the moment generating function for x sub 1 plus x sub n minus n times mu over the square root of n times sigma, that moment generating function converges to the moment generating function of the standard normal, and that is e to the, it was t squared over 2. That's the moment generating function of standard normal. That's what we want to show. The way that we're going to show this is in cases, and the first case is going to be where mu is 0 and sigma squared is 1. Case 1. Okay? Then here's the first thing to notice. So note, the moment generating function of just x sub 1, or x sub I should say, over the square root of n. Just for one of them over the square root of n, remember this mu, is phi sub x sub I over the square root of n. Okay. Evaluated at t, and that is the expected value of e raised to the t times x sub I over the square root of n. That's what it is. Now, for this random variable, sequence of random variables, for this particular one, we'll call it the nth one, we know that mu is 0 and sigma squared is 1, so sigma is just 1. So we're really looking at x sub 1 all the way added up to x sub n over the square root of n. So that is the, in this case, what we want to show converges, the moment generating function for that random variable, converges to here in this case. So let us look at the moment generating function for just that part. So the MGF, moment generating function, of the sum of the x sub I, so here I runs from 1 to n, over the square root of n, it's equal to e, the expected value, of e raised to the t times the sum, as I runs from 1 to n, of the x sub I over the square root of n. And that's equal to the expected value of e times t, e raised to, not times t, e raised to the t times x sub 1 plus x sub 2 plus x sub n, and each one of them over the square root of n. And then we can rewrite that expected value of that e to the power as the expected value of e, of the product of these, the different powers. And that's what I'm going to do next. So by rules of exponents, all I'm saying is this is the same thing as the expected value of e to the t times x sub 1 over the square root of n times e to the t x sub 2 over the square root of n times, and we keep multiplying all the way up to e raised to the t times x sub n over the square root of n. Now, what we know are the x sub 1s are, the x sub 1, x sub 2, x sub n, they're independent. So the expected value of the product of these functions will be equal to the product of these expected values. Times e t x sub 2 over the square root of n. Oh, I'm sorry, I messed up. So it's the product of the expected values because of the independence. Now, each one of them is identically distributed, so the expected value for each one of these things is the same. So this is equal to the expected value, if you will, of t x sub 1, just one of them, square root of n, all that raised to the nth power. But this expected value is nothing more than the moment generating function of x sub 1 evaluated at t over the square root of n. And then it's raised to the nth power. So in this case, so we want to show that the limit as n goes to infinity of this, the moment generating function of x sub 1 evaluated at t over the square root of n, raised to the nth power, that is equal to e raised to the t squared over 2, the moment generating function for the standard normal. Okay, that's what we need to show. So here we've got to do some work for this guy. Well, the first thing I'll say is this. Note, the limit as n goes to infinity of t sub x sub 1 of t over the square root of n raised to the nth power. So this is a limit. Now look, as n gets really, really big, the square root of n gets really, really big. T is a fixed value. This fixed value divided by something huge, getting bigger and bigger and bigger, goes to 0. Phi sub x sub 1 evaluated at something near 0, that's going to, well, what's phi of 0? It's going to phi of 0. What is phi of 0? Well, that's the expected value of x raised to 0, but x raised to 0 is expected value of 1. Expected value of 1 is just 1. This goes to 1, and as n goes to infinity, it goes to 1 to the infinity. That's an indeterminate limit form, an exponential indeterminate limit form. And the way that we handle that is we translate the problem into a problem for which we can use L'Hopital's rule. So you might remember L'Hopital's rule from calculus. Handles indeterminate limit forms of 0 over 0 or infinity over infinity. And that's what we're going to work towards. Okay, so what we do is we consider the limit as n goes to infinity, not of our original problem, but ln of our original problem. So ln of phi sub x sub 1 of t over the square root of n, all that raised to the nth power. So ln of that. Now, what we notice is that the limit as n goes to infinity of ln of phi, that's a phi, x sub 1 of t over the square root of n raised to the nth power is the same thing as, by rules of, or by properties of logarithms, I can bring this n down as a factor. So the limit as n goes to infinity of n times ln of phi sub x sub 1 of t over the square root of n. And if I look at this limit problem, this one, we've already talked about, well, first of all, when n goes to infinity, then that's going towards infinity. Now, we've already talked about as n gets really big, square root of n gets really, really big as well. And when you take a fixed number and divide it by something really, really big, that goes to 0. Phi of that's going to go to 1. Ln of 1 is 0. And this is multiplication, so we have infinity times 0. That's an indeterminate limit form as well. But the way that we handle that indeterminate limit form is that we'll put one of these functions, either n or ln of this quantity, in the bottom so that I still have an equivalent expression, but maybe I'll have an indeterminate limit form for which I can use L'Hopital's rule. Now, what you put in the bottom matters, because sometimes you put something in the bottom and it doesn't help you. But in this case, if you rewrite this as the limit as n goes to infinity of ln of the moment generating function of x sub 1, evaluated t over the square root of n, all over, well, if I just put n here, they're not the same expressions, so rather I'm going to put n to the minus 1, which I have to put to the front, but that's the same, and that, remember, n to the minus 1 is 1 over n. The top is going towards 0 as it was before, I haven't changed it, but the bottom is n to the minus 1, that's 1 over n in the bottom, and as n goes to infinity, 1 over n goes towards 0. So this is 0 over 0. Aha! We're now in a L'Hopital's rule form. So what does L'Hopital's rule say to do to try to compute this? What it says is you take the derivative of the top over the derivative of the bottom and then take the limit. So I'm going to say this is the same thing. It's the limit as n goes to infinity. Well, the derivative of top. So it's ln of something. Derivative of ln of something is 1 over the something. Now I have to take the derivative of what we're taking ln of, so that's phi prime, so x of 1 of t over the square root of n. But by the chain rule, I've also got to take the derivative of t over the square root of n. Now what am I differentiating with respect to? It's with respect to n, that's my variable. So really this is t n to the minus 1/2, and when I take its derivative, it would be minus 1/2 times t to the n to the minus 3/2. Okay, that's that. All over n to the minus 1's derivative is minus n raised to the minus 2. That's what we have. Let's kind of clean that up a little bit. You know, this is really minus 1 over n squared. That's what that is. And you can think of that, you know, this part over this part. It's just going to leave an n to the minus 1/2 in the bottom. That's what's going to do. And so what I can do is rewrite this. As equal to the limit as n goes to infinity. The top is p prime of x of 1, p over the square root of n. Okay. I'll go real slow. Minus 1/2 t n to the minus 3/2, because I need it for me, over, this would be p of x of 1 of t over the square root of n times the flip of the bottom. So the flip of the bottom is minus, well, the bottom is minus n to the minus 1/2. So the flip of that is minus, or 1 over minus n to the minus, not 1/2, minus 2. I just need a little bit of algebraic help there. That's the limit as n goes to infinity. Here, this is p prime, the moment generating function's derivative. Evaluate t over the square root of n. Okay, this 2, oh, first of all, this minus cancel. This 2 would go to the bottom. There's a t in the bottom. There's a phi in the bottom. This n to the minus 3/2 and n to the minus 2 will cancel with each other, just leaving an n to the minus 1/2. A lot of it will cancel with each other. In the bottom. That's what I get. Now, if we take the limit as n goes to infinity, here as n goes to infinity, square root of n gets really big. T divided by something really big goes towards 0. The derivative of the moment generating function evaluated is 0. It's nothing more than the expected value of x, but in this case that's mu, and in this case that's 0. So this part's 0. The bottom here, this is 1. So this is 2t. Okay? But n to the minus 1/2, that's 1 over the square root of n. As n gets really huge, that goes towards 0. So we still have 0 over 0 indeterminate limit form. So I take L'Hopital's rule again, and now it's going to yield an answer. This is the limit as n goes to infinity. So I use L'Hopital's rule again. It says take the derivative of the top. Okay, the derivative of the top is the second derivative of the moment generating function. Evaluate t over the square root of n. But then I have to multiply it by the derivative, by the chain rule, of t over the square root of n. I'm differentiating with respect to n. So again, that's t. You know, I don't know why I wrote a t here. The t is here. Okay, the t is in the top. This is a mistake. Okay, make that change. Okay, so there was a t here. Oh boy, what a mistake. Yeah, that t is in the top. So that t is this t. Now I'm taking the derivative of this. It's t times minus 1/2 n to the minus 3/2. That's what I get. Now, I have to take the derivative of the bottom. Here is one function, has n in it. Here's another function, has n in it. So we're taking the derivative with respect to n, so I can use the product rule. So I write down the first. Take the derivative of the second, which is minus 1/2 n to the minus 3/2. Aha, plus. Now, I write down the second, I did, and I take the derivative first, so 2 is still there. Here, the derivative of the first is the derivative of the moment generating function, evaluate t over the square root of n. Now I've got to multiply it by the derivative of t over the square root of n, and of course that's minus 1/2 t times n to the minus 3/2. These minus 1/2 n to the minus 3/2, this guy's got a t, but they appear at lots of spots. So they are factors in both the top and the bottom, and I can cancel them out. That's what I'm going to do. Okay, so when I cancel those out, what I'm left with is a limit as n goes to infinity. Okay. This is going to be the t times t in the top is t squared. It's the moment generating function's second derivative evaluated at t over the square root of n. Okay. that minus 1/2 n to the minus 3/2 cancels with those terms that are in the bottom. So in the bottom, I've got 2 moment generating function, evaluate t over square root of n. All right, plus, here I have, I think it is 2 times n to the minus 1/2. I've got a t left over, and then I've got the moment generating function's first derivative, evaluate t over square root of n. And that's what's left. Now, as n goes towards infinity, okay, this right here would go towards 0, as we've seen before, and we're taking the moment generating function's second derivative by evaluating 0. So that part is the expected value of x squared. Well, what's that? I don't know. Well, note the variance of x sub 1 squared. What's that equal to? That's equal to sigma squared, right? And by formula, that's the expected value of x sub 1 squared minus the expected value of x sub 1 to b squared. But in this case, we know the expected value of x sub 1 is 0. Okay? So that means, excuse me, so the expected value of x sub 1 squared equals to sigma squared, which in this case is 1. Okay? That's what we have. So this limit as n goes to infinity of t squared, the moment generating function's second derivative, the value of t over square root of n, all over exactly what we have here. 2, the moment generating function, evaluate t over the square root of n, plus 2 times n to the minus 1/2 t times the first derivative of the moment generating function. First derivative. I'm just rewriting it, okay? Let me handle this part. This first part, the top part, this part of the top goes to 1, so the top part goes to t squared. The bottom part, okay, so make this clear here. Look, as n goes to infinity, this goes to 0. Phi of 0 goes to 1. 2 times 1 is 2. Plus, here, this part right here goes to it's the expected value of x. So that's just 0. And this n to the minus 1/2 as n gets really big also goes to 0. So this part is 0. And so we get t squared over 2. Now, that was the answer to the limit as n goes to infinity of ln problem that we wanted to have. So the way to get rid of the ln's is raise our problem, use our problem, and raise e to it. And so our answer to our original problem is e to this answer. So, the limit as n goes to infinity of phi sub x sub 1 of t over the square root of n, all that was raised to the nth power. That's the guy that we wanted to compute the limit of it. Remember, we found the limit of ln of this guy, which was t squared over 2. So, the answer here is e to our answer for ln, so that's t squared over 2, and that's what we wanted to show in this case. All right. Excuse me. Case 2 is if mu is different than 0 or sigma squared is different from 1. So like we did with the proof of the strong law of large numbers, we're going to consider a sequence of functions x of I star defined by x sub I minus mu over sigma. Okay. Now, the expected value of x sub I star will be equal to the expected value of x sub I minus mu over sigma. The 1 over sigma can be pulled out because it's a constant. It would be times the expected value of x sub I minus mu, which is really equal to 1 over sigma times the expected value of x sub I minus the expected value of mu. That's equal to 1 over sigma, and the expected value of x sub I is mu, minus mu, that's 0, so we get 0 for the expected value of x sub I star. Okay. Now, we're going to work on the variance of x sub I star. So note, the variance of x sub I star, that's equal to the variance of x sub I minus mu over sigma, which is equal to the expected value of that, x sub I minus mu over sigma to be squared minus the expected value of x sub I minus mu over sigma, whatever that is, to be squared. But we calculated that, that was 0. So that's equal to the expected value, well, if you will, this is x sub I minus mu squared over sigma squared. I'll pull out the 1 over sigma squared. I'm left with the expected value of x sub I minus mu, but of course mu is the expected value of x sub I, and this needs to be squared. Hey, wait a minute, let me say that again. I'm taking the expected value of the random variable minus its expected value to be squared. Well, that's nothing more than the variance. So that's the variance of x sub I. That's sigma squared. So what I get is 1 over sigma squared times sigma squared, which equals to 1. Okay. Now, observe that the x sub I star will be independent because the x sub I star, and identically distributed random variables that's x sub I stars I'm talking about, each having expected value of 0 and variance 1. So I'm going to write that next. Each having mean mu equals 0 and variance equals to sigma squared, which equals to 1. So by case 1, what we have is that the distribution of x sub I 1 plus x sub 2 star plus x sub 3 star plus x sub n star all over the square root of n converges to the standard normal distribution. well, let's work with this. Note, x of 1 star plus x of 2 star plus all the way up to x of n star over the square root of n equals. We know that this converges in distribution to the standard normal distribution. What's this equal to? It's x of 1 minus mu over sigma plus x of 2 minus mu over sigma plus all the way up to x of n minus mu over sigma. All of the square root of n, which we can rewrite. So I'm just using algebra now. Well, this is going to be x of 1 plus x of 2 plus all that x of n. Then it was minus the mu's. How many mu's did we have? Well, we had n of them. And then we had in the bottom the sigma, but we also had that all divided by square root of n. So we might as well put square root of n down here with the sigma. And that's what it's equal to. So the distribution of that quantity, x of 1 plus x of 2 plus x of n minus n mu over square root of n times sigma converges to the distribution of the standard normal. That's what we wanted to show. All right, I want to do one example. Look, what I'm about to show is an example. It's an example of a problem type that's asked in statistics, and we hit it in probability, but it's really vital in statistics. It's central limit theorem. And they ask these types of questions a lot. So here's an example. It says 10 fair die are rolled. Okay? Find the approximate probability that the sum of the die are between 30 and 40. We're going to use central limit theorem to do this. So here's going to be the setup. We're going to let x of I be the output for the I die. So it's what row was. Okay? We want to find, to approximate, the probability that 30 is less than the sum as I run from 1 to n of the x of i's, which is less than 40. So to kind of get a good approximation of this, well, I think when we, in this case, when we mean between 30 and 40, here's what I think we're thinking about, that we include 30 and 40 here. And so what we're going to do is use a little lower approximation here. So to approximate this, we will use the central limit theorem to approximate. So this is what we want to approximate. The probability that 29.5 is less than or equal to the sum, this is 10, okay? What did I write before? I wrote down n. Let's go back. I should have written 10. We know what n is. So here, I thought this should be 10. Make that change. Okay. So this is 10 of the x sub I all the way up to, we'll make this less than 40.5. Well, this doesn't fit the central limit theorem. This is x1 plus x2 all the way up to x again. We need minus n mu all over square root of n times sigma. So I didn't know what mu is. So what is the expected value of x sub I? Okay. So what is this? This is a die roll, right? Well, it's the sum. So its output values, x sub I are 1 through 6 of the output values. So it's sum over the x sub i's, maybe that's n, let's call it j, running from 1, let's call it x sub I. X sub I running from 1 to 6, x sub I. Of x sub I times f of x sub I, which is the probability that big x equals that, x sub I. So this is 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3 plus 4 times f of 4 plus 5 times f of 5 plus 6 times f of 6. Where f of 1 is the chance that the die roll was 1. Well, that's 1/6. F of 2 is the chance the die roll was 2. That's 1/6. Each one of these guys is 1/6. So what this ends up being is 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. What is that? At 6, 11, 15, 18, 20, it's 21 over 6. 3 goes in both, it's 7 halves. Hey, on average, you get 3.5 for a die roll out. I also need to know the variance. To use the central limit theorem. Okay. Note, well, what is the variance by formula? Variance of x equals to the expected value of x squared, alternate that, minus the expected value of x to b squared, outstanding. We just figured this. So what's the expected value of x squared? Well, it's x sub i's here. The expected value of x sub I squared, so we're talking about die roll, that's the sum over the x sub i's running from 1 to 6 of x sub I squared times f of x sub I. Okay, so what is this? This is 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6 plus 4 squared times 1/6 plus 5 squared times 1/6 plus 6 squared times 1/6. That's it. This is going to be, the 1/6 can be factored out. We got 1 plus 4 plus 9 plus 16 plus 25 plus 36. Okay, so let me see here. That's 61, 67, 77, 86, 90, 91 over 6. All right, so variance of x sub I will be equal to 91 over 6, that's this part, minus 7/2 to b squared. I'm going to leave it to you to show that that's equal to 35 over 12. That's what we get. All right. Okay. So, the probability that 29.5, and this is what we're trying to find, less than or equal to x of 1 plus x of 2 plus all the way up to x of 10 is less than, it was just less than, 40.5. That's what we're looking for. Well, that's equal to the probability. Well, what I'm going to do is I need to get n times mu. Well, the mu was 7/2 and the n was 10. So that's 35 halves. It's 35 halves, 70 halves. Well, that's just 35. So I need to subtract 35 from all parts. So this is minus 5.5 less than x1 plus x2 plus x10 minus 35. So remember that's the minus n mu. Less than, when I subtract 35 here, I get 5.5. Same thing. Now I need the square root of n times the square root of 35 twelfths down here. So I'll do this. That's p divided by 5.5 over the square root of 10 times 35 twelfths. So 35 twelfths was sigma squared, square root of it is just sigma, so I'll put that down like that. Less than x1 plus x2 plus x of 10 minus 35 all over the square root of 10 times 35 over 12. Less than 5.5 over the square root of 10 times 35 over 12. Okay. This is equal to the probability. Now what this is, these ending numbers are the same. It's minus 1.02 approximately. It's less than what this is approximated by. So I shouldn't say equal. Well, look, this distribution, this random variable distribution becomes like the standard norm. So I'm just going to put z here. Okay, that's what we're looking at. And its approximation, I'll just put equal to here for a continuous random variable. It doesn't matter equal or not equal. So that's what I'm trying to compute. Okay, well, look, the standard normal, we have charts that help us figure this out for its probabilities. People have used computer, calculator to compute certain things. But our problem, let me write down this. So our problem is this. It can be thought of pictorially. So, well, it's really equal to, okay. So how do you figure out this probability for the standard? What you do is you integrate its PDF over this region. What's its PDF look like pictorially? What's the bell-shaped curve? Okay, that's what it looks like. And this might be minus 1.02. And this might be positive 1.02. And so we want to know the area under this curve between here. Okay, that's what it is. Well, that's equal to pictorially. So it would be the same thing as 1.02, the area underneath the curve from 1.02 back, minus the area under the curve from minus 1.02 and back. take away this area from that one. Now, our computations, a lot of times in tables, just deal with positive numbers in back. Okay, so this guy we can compute, but this guy, because it's not positive numbers, sometimes we have a little trouble with it. Not a little trouble. Some tables don't have that. So what I want to say is this is the same thing due to symmetry of this function. So 1.02's area under this curve in back minus, well, this region is the same thing as this area under this curve. So 1.02 and forward, because of symmetry of this function. Well, that's equal to this area under the curve minus, well, again, most of our tables, it's not true for all tables, but a lot of times the tables are from here back. But if you will, we can rewrite that as 1 minus this picture, this area. So this area right here that I'm looking for is 1 minus, because the area underneath this curve is 1. It's 1 minus this area. Okay, this right here is nothing more than the CDF of the standard normal, evaluated 1.02, minus 1 minus, again, this is the CDF of the standard normal, evaluated 1.02. So when you simplify this, you get 2 times the CDF, the standard normal evaluated 1.02, minus 1. Well, that's 2 times. You can look up on a table this value, and it's approximated by 0.8461 minus 1, and that is 0.6922. Approximately is what we get for our probability that the sum of the dies will be between 30 and 40. So that's what we get. And that's an application of the central limit. All right, that's all I wanted to cover today. And that concludes the material that's going to be covered on your first exam. Okay? Thank you very much for your time and patience.